Alright, so in this lecture I'm going to talk about a very important aspect in analysis, which is basic topology on the real line. This can be generalized to topological spaces of any sets. So this chapter actually builds the foundation for study of topology in the general case. Alright, so we'll be following Rudin's basic topology. So first comes the notion of finite, countable and uncountable sets. Now, there exists different kinds of infinities. A set can be either finite or infinite, but even in case of infinite sets, some infinities are larger than other infinities. So first, we'll start with the definition of equivalence relation. We know that a relation is a subset of a Cartesian product of two sets. So if A and B are two sets, a relation between them is a subset of A cross B. Now, this relation is reflexive if for all elements A related to B, for all elements in A, if small a is related to small a, or in the set theory, whole set theoretics term, we say that all of A is related to A. It is symmetric if A is related to B, then B is related to A. That is, if small a is related to small b, then small b is also related to small a. And it is transitive if in the set theoretic term whole of A is related to whole of B and B is related to C implies A is related to C, and we take the lowercase letters for the element wise formulae of these. Now if these three properties are satisfied, then we say that the relation is an equivalence relation, or in terms of mappings we can also say that A and B have a one-to-one correspondence between them. And if that happens, we say that A and B have the same cardinal number. Note, this cardinal number is a generalization of the cardinality that we study in school. Cardinality of finite sets is the number of elements in that set. However, if the set is infinite, then the number of elements, the notion of number of elements does not make sense. What makes sense is the notion of cardinality. We will see why these things are important. Consider now a set called Jn, where n is some positive integer. Jn consists of elements of the form 1, 2, n, that is n positive integers. And J without any subscript is the set of all positive integers. We say a set capital A is finite if A is equivalent to Jn, that is A has a one-to-one correspondence with Jn. So we can enumerate the elements of A as A1, A2, A3, that is small a1, small a2, small a3 and so on up to An. If we can do this, then we say A is finite. If not, we say A is infinite. Also, if A is equivalent to J, that is the set of all positive integers, we say A is countable. And if A is neither finite nor countable, that is, there does not exist a one-to-one correspondence with some Jn nor with some J, then we say A is uncountable. And A is at most countable. This is rarely used, but A is called at most countable if A is either finite or countable. So A is either finite or infinite, and if it is infinite, then there are two possibilities: countability and uncountability. We'll see that A is the countability is a smaller kind of infinity than uncountability. So countable sets, as I said, can also be called enumerable or denumerable because we can enumerate them. We can count them and enumerate the elements as first element, second element, and so on. Now, there comes an example which leads to a very important notion of characterizing infinite sets. Suppose A is the set of all integers 0, plus minus 1, plus minus 2, and so on, and J is the set of positive integers 1, 2, 3, 4, and so on. Now we set up a function f from J to A as follows. F of n is n by 2 when n is even and is minus of n minus 1 by 2 when n is odd. We can check that this is a one-to-one correspondence between J and A. Now we see that A is an infinite set. A over here is an infinite set, and so is J. But A is a bigger set because it contains all integers, and J is a smaller set because it contains only the positive integers. So J is a proper subset of A, but still A is equivalent to J. That is, A has a one-to-one correspondence with J. So A and J have the same cardinal numbers. This leads to a very important notion in infinite sets, that is, an infinite set is equivalent to one of its proper subsets. This is not true for finite sets. So we can replace this definition 2.4b by saying A is infinite if it is equivalent to one of its subsets. This is a definition and that is another definition. A is infinite if it is equivalent to one of its subsets. The proof of this is a little tricky. But we see from example that this happens over here. We can form a function. We can take an infinite set and we can form a function such as left shift operator or something, and we can still get a proper subset to which the original set is equivalent to, has a 1-1 correspondence with, for countable sets. So for the countable sets, we can prove that for any countable set there exists a proper subset to which it has a 1-1 correspondence. For uncountable sets also we can do in a similar fashion. And I leave the proof to you. Now what do we mean by a sequence? A sequence is actually a function. Function from the set J of all positive integers to some target set, to some codomain. So if the domain is positive integers, then we say that such a sequence is a function, and we sometimes denote such a function is a sequence. I'm sorry. So such a special type of function is called a sequence if the domain is positive integers. And we also denote sequences by the images. So f of n can be written as xn, and a sequence can be denoted in this fashion in curly braces xn, or sometimes as x1, x2, and so on. And these xn's are called the terms of the sequence. And n's belongs to J, as we know, and these xn's is said to be a sequence in A if the codomain is A, or we also say a sequence of elements of A. This is a proper way of saying it, but will not be so formal always. Anyhow, now note that in sequences it is different from any other set in the sense that it can be a multiset. The images need not be distinct. For example, if I take a continuous function, a constant function, then the sequence consists of just one element of the range. Suppose f of something is f of n is c, then the sequence is c, 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 and so on. Now, there comes another important theorem which states that every infinite subset of a countable set is countable. So, this theorem tells us that countability is smallest kind of infinity. There does not exist a smaller infinity than the set of countable sets. And no uncountable set can be a subset of a countable set by this theorem. So how do we prove it? Suppose we take E a subset of A where E is infinite and A is countable. Now we arrange the elements of X of A in a sequence xn of distinct elements. And now we construct another sequence nk as follows. Let n1 be the smallest positive integer such that xn1 is in E. Having chosen such integers n1 to nk minus 1, let nk be the smallest integer greater than nk minus 1 such that xnk is in E. Now if we put fk to be xnk, we obtain a one-to-one correspondence between E and J. This means that we enumerate the elements of these subset E. That is, there exists a one-to-one correspondence between E and J by this kind of enumeration. And with the idea of induction, we know that this happens for every k. Thus, we get E, which is any arbitrary subset of a countable set A, and if E is infinite, then E is countable. So, every infinite subset of a countable set A is again a countable set. Now we come to the definition of union, intersection, and so on. Here it is given that A and omega are two sets, and with each element alpha of A there is associated a subset of omega which we denote by E alpha. Now the set whose elements are the set C alpha will be denoted by, so this is a set of sets. Oh, now there exists some pathologies concerning set of sets. So we instead call them a collection of sets or a class of sets, sometimes a family of sets and so on. This is because there might not exist a set of all sets. Russell's paradox and all those pathologies exist in set theory. So we avoid such pathologies and call the collection of sets or class of sets, not a set of sets, because a set of sets might not exist. Anyhow, the union of these sets E alpha, where alpha is in some index set A, is, as we know from high school, we write all the elements together. Now, to say rigorously, we say that the union of sets E alpha is defined to be the set S such that X belongs to S if and only if X belongs to E alpha for at least one of alpha in A. So, every element in the union set has to belong to at least one of the sets of which we are taking the union, and we use this familiar notation. There can be a finite union or an infinite union. Now intersection can be similarly defined. Some element X is in the intersection set P if it belongs to, if and only if that element belongs to every E alpha. And if A intersection B, where A and B are two sets, if it is non-empty, we say that the sets intersect. Otherwise, the sets are disjoint. Examples of these things are pretty straightforward. Now, union operation, as we know, is commutative, and so is the intersection. Similarly, these operations are associative. There also exists a distribution law, which we have done earlier in school. There, this is something which is given in school books, but we do not rigorously prove it most of the times. So, one way to prove uh, identities in set theory is by using the property called Auson-Darung's axiom, which says that two sets are equal if and only if they have the same elements. And A is equal to B in this way can be implied from the axiom as A is a subset of B and B is a subset of A. So, while proving equality in set theory, we use this notion where each side is a subset of itself. So, we pick some element in one of the sides and show that the element belongs to the other side, and similarly, we do vice versa. That is what is being done over here. We take the left and right members of this equation 10 as E and F. We pick up some element in E. Then X belongs to A intersection B union C. This means that X belongs to A and X belongs to B union C because it is in the intersection, so it must belong to both. Which means that X belongs to A and X belongs to either of B or C. So, by parsing this English sentence into mathematical sentence, we say that X belongs to A and X belongs to either of B or C is the same as X belongs to A and B, or X belongs to A and C, because X belongs to A and B or C. So this means that X belongs to the right hand side F. So E is a subset of F. Again, proving the other way, we suppose that some arbitrary element X belongs to the right hand side F. This means that X belongs to either A intersection B or A intersection C. That means that X has to belong to A because it belongs either here or here. And moreover, X has to belong to one of B or C, at least one of B or C. So X has to belong to A and at least one of B or C. And this, when translated to mathematical notion, gives me X belongs to A intersection B union C. So that again the right hand side is a subset of the left hand side, F subset of E. And using this F subset of E and E subset of F, we can show that we know that E is equal to F. Thus, the distribution law follows. And there are some few more easy implications which can easily be verified. The A union some empty set is again A. A intersection empty set is the empty set, so on. Now, a theorem which states that let En for n belonging to natural numbers be a sequence of countable sets, and we take a union, infinite union of these countable sets, then S is countable. This means that any arbitrary union of countable sets is countable. How do we prove that? We make an array of elements of En in this way and we enumerate them diagonally. So let every set En be arranged in a sequence as x and k, for k equal to 1, 2, 3 and so on. So here are elements of E1, E2, E3 and so on. In this way we can write all the elements in the union S. Now we start counting in this fashion. We first take the first element as x11, then the second element as x21, third as x12, fourth as x31 and so on. In this way we will cover all the elements in the set S. So we will have an enumeration of S. That means we will have a one-to-one correspondence with J. S is equivalent to J. Or more precisely, X has a one-to-one correspondence with a subset of J. So we know that S is at most countable. We take a subset of J because there might be overlaps. So the two elements of En of different Ens can be equal for different N's. So we take a subset of J to have a one-to-one correspondence. So we know that if some set has a one-to-one correspondence with a subset of J, then that set is at most countable, maybe finite or maybe infinite, but at most countable. Now, since E1 is a subset of S, because E1 lies here and S is a union of all those E, so E1 is a subset of S, and we know E1 to be infinite. Then this means that S is also infinite, and S is at most countable, and infinite means that S is countable. It is not finite, so it is countable. Hence, we see that a union of countable sets gives me a countable set. And we have a simple corollary that if A is at most countable, and for every alpha in A, B alpha is at most countable, then T, which is the union of all those B alphas, then T is also at most countable. And this T is equivalent to a subset of this S. This can be proved in a similar fashion. In a similar way, we can show that if A is a countable set and Bn the set of all n tuples A1 to An, where Ak's belong to A. So this in analogous to Euclidean notion, this can be written as A to the power n. And the elements A1 to An, which need not be distinct, then Bn is countable. So this theorem is very important. If I take a Cartesian product of countable sets, then that product is countable. This theorem will give me that the set of rational numbers is countable. So how do I prove this? B1 is countable because B1 is just A. Now we use the principle of mathematical induction. We have the base case. Now suppose Bn minus 1 is countable. And now we take Bn. Elements of Bn then are of the form B comma A, where B belongs to Bn minus 1 and A belongs to capital A. Now for every fixed B, the set of pairs is equivalent to A, because as we move about whole of A, this is same as moving about capital A. So B is fixed, A varies, and each A there can be a function which is just a projection of this B comma A to A, capital A, and that will be a one-to-one correspondence. And thus we see that Bn is the union of a countable set of countable sets. And by the previous theorem, we see that Bn is countable because Bn minus 1 was countable. Here we are fixing a B. Now for each such B, we get Ba as equivalent to capital A for each such B. As we move about B, as we now as we vary B, we get a union of countable set of countable sets. So Bn is countable, and since n was arbitrary, this follows by induction that this holds for every n. Now, a corollary, as I said, is that the set of all rational numbers is countable. We take n equal to 2, and rational numbers of the form b by a can be written as a set of ordered pairs as two tuples, and thus it follows. We will also see in the exercises that the set of all algebraic numbers is countable. We will get to know what algebraic numbers and transcendental numbers are. But there exists infinite sets which are not countable, like real numbers, complex numbers, and so on. How do we show that? Now, consider a set A, the set of all sequences whose elements are the digits 0 and 1. So, a binary kind of sequence. Only two possible values, 0 and 1. So, elements of A are sequences of this form 1, 0, 0, 1, and so on. We will show that A is uncountable. How? Let E be a countable subset of A, and E consists of sequences S1, S2, S3, and so on. Now we construct a sequence, another sequence S as follows. If the nth digit in Sn is 1, we let the nth digit of S be 0, and vice versa. So we take the complement of the digits at each position. So S is a sequence where if there were 1 in the first position in S1, then S will start with 0. If the second entry in S2 is 1 or 0, then the second entry in S will be 0 or 1 respectively. Similarly, complement of the third position of S3, and so on. Then this sequence, we see that this sequence S will differ from every member of E in at least one place, because S, the elements of S is not equal to S1 because it differs in the first position of S1. So S is not equal to S1. S again is not equal to S2 because even if all the other entries of S were equal to S2, the second entry of these S and S2 are not equal because they are opposite of each other. Similarly, the third entry of S and S3 are not equal because they are opposite of each other. If this were 1, this would have been 0. If this was 0, this would have been 1. So S differs from every element of E in at least one place. Thus, S does not belong to E, but S is clearly in A because it just is a sequence of the form 0 or 1, 0 or 1, 0 or 1, and so on. So we see that E, which is a countable subset of A, is a proper subset of A. So E. So now E is arbitrary countable subset of A. So any countable subset of A is a proper subset of A. So this means that there exists sets or which are not countable. So A is not countable. So A is uncountable because any countable subset of A is a proper subset of A. Now this idea was first shown by Cantor, Georg Cantor. Now real numbers can be written in base 2. That is binary representation of real numbers. And real numbers can be written as sequence of zeros and ones. We can even approximate an irrational number by a sequence of zeros and ones too, and we can get to a precision to as much degree we want, and an infinite sequence of zeros and ones will depict an irrational number or some fraction which is rational number. So even real numbers can be depicted in sequences of this form, and from this theorem we get that a set of real numbers is uncountable. Now comes the very important notion of metric spaces. With the help of this notion, we will understand what distances are. How can we attach the notion of distances to sets? We are used to the notion of distances. We are used to using the notion of distance in the Euclidean space. Now we will get to know how rigorously we can attach the notion of a distance or metric on some set. So the definition is for any set X whose elements we shall call points. This set is said to be a metric space if with any two points P and Q in X there exists a real number D, D of P and Q, called the distance from P to Q, such that D of PQ is always greater than 0 if P is not equal to Q, and equal to 0 if P equal to Q. And D of PQ is equal to D of QP. The distance between 2 points does not change when we move from one point to the other, first point to the second point, or second point to the first point. And it has a triangle inequality. That is, distance from PQ is always less than distance from PR plus the distance from RQ for any R in this set X. So any set with these three properties is called a metric space. And this D, the function from the set X to the real numbers, this gives me a function which is also called a distance function or metric. Now, there exists different kind of metrics on the sets which we are familiar with. There are different kinds of metrics on real numbers. There are different kinds of metrics on Euclidean spaces. One of the most usually seen is this metric dxy, which is mod of x minus y. That is the absolute value. Now we see that any subset of a metric space is a metric space in its own right. Unlike algebra, this subset is also a submetric space in some sense without any additional checking. The metric structure is inherited by the subset. Now, this is just a rigorous way of denoting what these open intervals, closed intervals, semi closed intervals are. Another notion is that of an open ball. What is an open ball or a closed ball? Suppose X is in the Euclidean space Rk and small r is greater than 0, is some radius. So open ball B with center X and radius r is defined to be the set of all y's in Rk such that the distance between y and x is less than r, and it is closed if this distance is less than equal to r. So think of it as a ball whose center is at x, and the ball consists of all those points which are r distance away or less than r away from x. If we include r, then it is a closed ball. If we do not include r, then it is an open ball. And another notion is that of a K cell. If ai is less than bi for some set of natural numbers I, all those points x in Rk whose coordinates lie between ai and bi, so x, x1, x2, xk, whose coordinates x1 lies between a1 and b1, x2 lies between a2, b2, and so on, that set of points is called a K cell. So an interval is a one cell. This closed interval a comma b is a one cell. A two cell is a rectangle, and so on. Now, a set is called convex if this happens. For any 2 points in the set, the line segment lambda x plus 1 minus lambda y belongs to E, for lambda belonging to this open interval 0, 1. This is a rigorous way of the geometric notion of convex figures like balls and rectangles, circles, and so on. We take any 2 points, join them by a line, and that line wholly lies in the geometric figure. So, this is what it is. We can rigorously show that balls are convex rather than geometrically drawing, taking points and drawing lines, which is not a rigorous way to show because we cannot take every point and draw lines between them. An algebraic proof is such. We take 2 points, x and y, we take another point z and a lambda between 0 and 1, and we consider this expression lambda of y plus 1 minus lambda of z, the line joining y and z, and its distance from x. Now after rearranging, we get lambda of y minus x plus 1 minus lambda of z minus x. And this, by the triangle inequality, is less than equal to lambda of y lambda mod of y minus x plus 1 minus lambda can be pulled out as lambda is less than 1 mod of z minus x. This we know to be the first expression we know to be less than lambda r, because y minus x is less than r, because they lie in a ball. So this expression is less than lambda r plus 1 minus lambda r. And after solving this, we get that this is less than r. So this line lies in the set in the ball. So we can use the similar proof for closed balls. And K cells, the convexity of K cells also easily follows. Now, these are the important topological notions: neighborhood, limit point, interior point, and so on. We consider X to be a metric space. What is a neighborhood of some point? A neighborhood of P is a set NRP consisting of all Q such that distance between P and Q is less than R for some R greater than 0. The number R is also called the radius, and it is denoted as NRP, this neighborhood. Now a point P is a limit point of some set E, where E is a subset of this metric space X. If every neighborhood of P contains a point Q distinct from P, such that Q is in E. So a limit point might not belong to E. It can be outside E, but it will have a neighborhood which non-trivially intersects with E. No matter how small a neighborhood I take, how small an R I take, it will still intersect in a distinct point, distinct from P, with E. Now if P belongs to E and P is not a limit point of E, then P is called an isolated point. That is, you take a set and you take another point away from it, then that point is not a limit point, because there exists a ball around a neighborhood around P which does not intersect any other point of E other than itself. So there does not exist a distinct point, and thus P is not a limit point, and so P is called an isolated point of this set E. This is a very important separability condition, and it can be specified when studying topology. An analogous situation arises called the Hausdorff space, which is for later on. Anyhow, now a set E is closed if every limit point of E is a point of E. So, if a set consists of all its limit points, then that set is closed. A point P is called an interior point if there exists a neighborhood of that point such that that neighborhood totally belongs to the set E. So an interior point is something which has a ball, a neighborhood around that point which wholly lies inside the set. And E is open if every point in E is an interior point. So E is open if for every point we can find a ball wholly lying in E. What is the complement of a set? So complement of a set is all those points which do not lie in the set. What is a perfect set? A set is perfect if the set is closed and if every point of the set is a limit point of the set. So E is perfect if E is closed and if every point of E is a limit point of E. There are no isolated points. The set is closed without any isolated points. All points are limit points. The E is said to be bounded if there exists a real number m and a point q in the bigger set X such that distance between p and q is always less than m for all p in E. So, so no matter what point I take in E, distance of that point from some fixed point in the bigger set X always has to be less than some number m. Then that set will be called as bounded. And a set is said to be dense in X. E is dense in X if every point of X is a limit point of E or a point of E, or maybe both. So some subset is dense in a superset if every point in the superset is a limit point of the subset, or it is a point of the subset, or maybe both. The condition that both happens does not harm. So density is a very important notion. Every point in the superset must be a limit point of the subset, or maybe a point of the subset. We will see that rational numbers are dense in real numbers. There exists a rigorous proof that neighborhoods are open sets. This can be proved using triangle inequality. This is also a very important notion which follows from common sense mainly. If P is a limit point of a set, then every neighborhood of P contains infinitely many points of E. Because suppose we have a neighborhood n of P which contains only a finite number of points of E. Let Q1 to Qn be those points in this intersection n of E which are distinct from P. Now if we take the minimum distance of P from these Q's, that is R is minimum of D P Q M where M lies between 1 and N. Now if we take a neighborhood NRP, then this does not contain any point of E which is distinct from P. So if we take a smaller neighborhood which is less than the radius of the nearest point from P, then that neighborhood will not contain anything of E other than maybe P. So that only has a trivial intersection. And this contradicts the the notion, the supposition that P is a limit point, because every neighborhood must contain a non-trivial intersection with E, and thus we see that there can exist only exist infinitely many points of E in every neighborhood of P. And the corollary of this is that a finite point set has no limit points. Because if it would have been, it would have been a direct contradiction of the our theorem. Now, these examples can easily be proved, which we will see next time.